Alright, hello everyone. Today we're going to be looking at TLC, or thin layer chromatography. Alright, let's get into it. Alright, so basically the way thin layer chromatography works is we have a substance. Specifically, we're going to be looking at amino acids. We have an unknown amino acid that we're going to put into a solvent. Alright, and then we're also going to have some filter paper, and we're going to measure how far that unknown amino acid moves along the filter paper. We're also going to measure how far the solvent moves along the filter paper as well. Alright, so let's go through that a little bit more now. Alright, so basically the way it works is we put filter paper, alright, which is this orange rectangle here. So this is the filter paper. Okay. And that's going to be associated with the stationary phase. Okay. We'll talk a little bit more about that in a second. Okay. So we put it in this sealed container, alright, with a little bit of solvent as well. So this line here represents the solvent, okay? And that solvent is going to be associated with our mobile phase. Okay, so what happens is we take a little dot of the unknown liquid, or unknown amino acid, and we're going to put that unknown onto the filter paper down at the bottom. Alright, so we take this unknown and we're actually going to put it right here. Alright, we take a little dot and we put it right here. Let's call it substance A. Alright, let's say that's substance A there. Okay, so the filter paper is actually going to be highly polar. Okay, so it's going to have a high charge associated with it. So it's going to be polar. Okay, and the solvent down the bottom here, this is going to be less polar. Okay, so it still can have a charge, but it's just going to have a lower charge. Okay, so it's going to be less polar or less charged. Alright, so what's going to happen now is, because this filter paper is porous, so it allows the solvent to flow through it, the solvent's going to move from the bottom here. It's actually going to move up into this filter paper here. So what's going to happen is the solvent will move up this way, okay, and it might stop about here. Alright, so let's say it moves up to this point here. So the distance that that solvent travels, that's going to be associated with the mobile phase. Alright, so let's just say this solvent here, it moves to this point. Now we measure the distance that that solvent moves. We measure it from the point of our unknown amino acid. So it's actually going to be represented by this distance here. Okay, so from that point of our unknown amino acid, it's going to move from there to there, right? And whatever that distance is, that distance actually represents the mobile phase, or the distance the solvent has moved. So when that solvent moves, it's also going to move our unknown liquid as well. So this A here, this can actually move up here as well. So it might end up over here. Okay. Now the distance that this molecule moves depends on the charge of the amino acid. If that amino acid has a higher charge, it's actually going to move less than if it had a lower charge. So the distance that substance A moves That's referred to as the distance that the solute moves. Okay, so this distance here equals distance that the solute has moved. Alright, so that distance there is the distance moved by the amino acid. Okay, so now we have these two distances here, right? This distance and this distance here. And we are going to use that in our retention factor formula. So this is a retention factor here. This formula is in the formula book, so you don't have to memorize it, but you probably have to know how to apply it. Okay, so retention factor is equal to the distance moved by the amino acid, this distance here, divided by the distance moved by the solvent, this distance here. Okay, and some key things this can tell you about amino acids. A higher retention factor indicates that the amino acid has a less polar side chain. So remember in our video about amino acids, I was talking about how the backbone, or that top part of the amino acid, stays the same. The part that changes is that side chain. So those side chains can have different properties, including different polarities. So if we have a lower polar side chain, then we will have a higher retention factor. All right. So if we have a less polar side chain, then we will have a higher retention factor. If we have a more polar or charged groups on the amino acid, then we'll have a lower retention factor. Okay, so that's kind of the process that you're expected to explain in your syllabus. Explain how the reaction takes place and where these distances here are measured from. So remember that the distance moved by the solvent is measured from the point that we add that amino acid. So it's not measured from the point that the liquid goes up to on the filter paper. It's measured from the point from that amino acid to wherever that solvent stops moving up the filter paper. Okay, and then also the distance moved by the solvent or the distance moved by the amino acid, just from that point to that point there. Okay, all right. So that's pretty much a quick summary of thin layer chromatography and what retention factors mean and what they can indicate. All right, if you have any questions, let me know. Thank you.